Stan Gibilisco here with installment number 6 in the complex number primer. I am going to show you how to add two complex numbers in general. And then we'll look at a specific example. Remember that the J operator is defined as the positive square root of -1. And in engineering applications, we write the coefficient after the letter J. A, B, C, and D are real numbers, and J is the positive square root of -1. In this general expression, A, B, C, and D can each be any real number whatsoever. Negative, positive, or 0. When we add two complex numbers like this, we add the real portions and the imaginary portions separately. In this case, we get, and I'm going to add some extra parentheses here to emphasize that here is the real part, JB plus JD. If you'll remember your distributive rule from pre-algebra, we can take the J out and modify the equation so that we get that. So we simply add the real number parts of the complex numbers together and the imaginary parts together. Now that may look a little arcane and confusing, although it's straightforward enough, and we can produce an example. Let's consider, for example, the complex number 3 plus J4 and the complex number let's say -4 plus J3. When we add these together, we get 3 plus a -4, which is a -1, plus J7. That is the sum of these two complex numbers done arithmetically. Let's look at that in vector terminology, or in the complex number Cartesian plane, where we put A on the horizontal axis and JB, the imaginary portion, on the vertical axis. The real number portion that way, the imaginary number portion that way. 3 plus J4 might look something like this. And -4 plus J3 will go down like, let's see, -4 plus J3 will go down kind of like this. No? I've got that messed up. -4 goes out this way, plus J3 goes up like this. -4 plus J3. Now, you may remember from your vector addition classes, if you've had any vector addition, that you can add them geometrically by forming a parallelogram. If you don't remember that, I'm going to show you how to do that now. Consider these two vectors as two adjacent sides of a parallelogram. Then we construct the third side equally long with that vector and parallel to it, and the fourth side equally long to that vector and parallel to it. Now we have a parallelogram. Opposite sides are parallel. This pair of sides is parallel and that pair of sides is parallel. We can represent the sum of two vectors geometrically by drawing the diagonal of that parallelogram, and in this case that vector corresponds to -1 plus j7, which we can intuitively see from this graph, even though I haven't graduated the scales precisely. That's how you add complex numbers vectorially in the Cartesian system. Now, if you want to use the polar system, where you would start with an origin, put the positive real number axis going to the right, and then define angles going around 90 degrees, 180 degrees, 270, and consider the angle theta. So if we have a vector, say, going up like this, we have a radius r and an angle theta, and we can represent that as theta r, or if you prefer r theta. Depends which one you want to call the independent variable. We've been through this in previous episodes of this primer, but I'm just reiterating it now. If you want to try and add two vectors in the polar system directly, you can't do it that way. You cannot add the angles and add the radii and expect to get a valid result. It doesn't work that way. If you want to add these vectors in the polar plane, the best way to do it is to convert to the Cartesian forms and then add them, and then convert the Cartesian forms back to the polar forms. That's a little bit tedious, but sometimes that's the only way to go. If you want to get a little more information about how to do that, you can find it in this book, Pre-Calculus Know-It-All. And I'm going to look for chapter 6 begins on page 90. It gets into complex numbers, how they behave, how to add them, how to multiply them. Then it gets into complex vectors on page 101. And then the Cartesian to polar and polar to Cartesian conversions are described on pages 102 and 103. You can't really see them here, but this is a comprehensive pre-calculus book, just about 600 pages long, and it's part of a trilogy or set of 3 books that I wrote, intended for supplemental texts for homeschoolers, and if you just want to study a little more about algebra, pre-calculus, and first year calculus. 3 books. They're all called the Know-It-All series. Know-It-All. My nephew helped me proofread the text for one of these books, and he liked to call it, actually he helped me with pre-calculus, and he liked to say, well, you know, it doesn't cover everything. You can't cover everything in a paper book anymore, not competing with online content that can be millions of pages long. So he called it pre-calculus Know-It. Pre-calculus Know-It. Well, that's good enough for me. I would recommend that you study this book to get a good grounding in complex numbers if you haven't had it before. That's where they usually teach complex numbers, is in pre-calculus, also sometimes called analysis, somewhat erroneously, usually in about the 10th or 11th grade in high school. With that, I will end this episode of the Complex Number Primer and sign off. So long.